Good morning, Michael.
Good morning, Matt.
What is this? L'Hopital's rule. This little funny thing over the O
Yes.
replaces an S. So you can call this hospital's rule. He was a Frenchman.
He was a Frenchman. I guessed that by the accent.
And the accent, now what happened? Well, at the time of the French Revolution, for some reason, there were certain words that the Revolutionary Committee didn't like. So OS, after some O's, they got rid of the consonant after, which was an S, and put the
little hat.
little hat on it.
Which makes sense, because in French you say l'hôpital, and I don't hear an S in there. Do you?
And the same with the French word fenêtre,
Okay.
because the second E has a hat, because it was fenestra, which is like the Latin fenestration.
Fenestration.
So it's really interesting. So we'll say hospital's rule is okay,
There
or
you go.
l'hôpital's rule is okay, depending if you're a Frenchman or royalty from before the French Revolution.
There we go. So do you know, have you seen sort of the classical definition or statement of l'hôpital's rule?
I'd like to see that.
Well, the problem with this classical statement is it uses limits. And in our approach, we've been avoiding the word limits as much as we could because we don't feel they're necessarily intuitive. But this is such a standard result, I think we should at least write it down how you normally see it in a textbook, and then we'll write it in our form.
Okay, let's see the usual way.
So it involves a limit. Let's say x going to a of f of x over g of x is equal to the limit of f prime of x over g prime of x under certain conditions. Okay, and what are the conditions? Well, first of all, f and g should be equal to 0 at x equal to a, because that gives you this problem. You have a sort of a 0 over 0. You can go, I don't know what to do here. So if what? So we want f at a is equal to g of a is equal to 0. That's one condition. The second condition is g prime. Well, actually, f and g should both be differentiable. Okay, they just have to be differentiable near a. I'll just say differentiable. And the third thing is we want g prime of x to not be equal to 0.
So, Michael, in doing all this, this is a new idea. Like we've been looking at nearness and neighborhoods of a reference point, and we've looked at differentiating many things, and we've looked now at interpolating. And so this is kind of something we haven't looked at before.
Right. We haven't talked about exactly what we mean by a limit. In our language, what we would say is we give a name to this number. Let's call it L. But what our way of saying this would be saying that f of x over g of x is approximately, sorry, I shouldn't erase with my finger. Okay. We want to say f of x over g of x is approximately equal to L. So what we'll say, it's equal to L plus a small error term.
And this means the error near x equal to a, right?
Yeah, this error is the error, sort of the difference between these two things. That's the error. And as x gets close to a, this gets close to 0. Okay, so basically the error goes to 0.
And we kind of know that intuitively because the function just near L isn't going to do something weird,
Right.
like jump to infinity.
And so the statement is saying this is equal to that, provided, first of all, we have all these conditions, and that this ratio is approximately equal to L. So the order is important. Finish writing it out. The order is important. What we do is say, if this approximation is true, then this approximation is true,
Given the conditions above.
given those conditions above.
All right, so now,
Can I give you a quick example just to sort
sure,
of show
let's
you?
do a simple example.
So if you look at sine x over x near 0, you say, well, is that approximately equal to 0 over 0? That doesn't make any sense. Okay, so you don't do that. You say, I'm going to use L'Hopital's rule. All the conditions are satisfied. And we say, okay, the derivative of sine is,
Cosine.
and the derivative of x,
1.
1. And we know, well, we know from all sorts of reasons, but even, for instance, our Taylor polynomials, this is approximately, so this is very much equal to 1 plus some error function that depends on x. So that tells me that this is very close to 1. So it's equal to 1 plus some error function. Maybe I'll give these guys different names, 2, 1. Okay?
Yeah,
So sine x over x for x small is very, very close to 1.
that's a good start. Now, can we prove it and look at it geometrically? Because that's the real piece in most of the discussions you see in texts that is not often referred to. And we are in good shape to do this.
We are in good shape because, you know, if you look at this, you say, hey, I remember seeing something like this before. If I put an f of x minus f of a g of x minus g of a, you kind of go, that looks like the mean value theorem.
Secants.
We can use secants. So can I draw a picture for you?
Yeah, let's do that.
Look at all the space we've got here. So here, I'm going to draw a little curve. Here's the point 0, 0. I'll have a little curve. Okay. And what is this curve? This is the curve x and y, described as x is the g. I'm going to think of it as a function of time. G of t, f of t.
Oh, we did that before when we looked to extend the mean value theorem to the Cauchy version.
To the Cauchy version, exactly. So if I take a point on this curve, like let's say this point here, okay, this is, the x value is g of t. So this is my x coordinate. The y value is f of t. Notice I have here, this is f at, this is e, g at a, f at a. So remember, I had these that they
Oh, they're going
equal
to
to
start.
0, right?
We're going to A is going to be 0.
Yeah. Now the ratio f of x over g of x is overrun.
Right?
So maybe I'll use my pink crayon. So that's,
Well, we know this. That's straightforward, right?
this
It's a
slope.
Yeah.
Slope. F of t over g of t, right?
What
So
about,
rise.
because G of A and F of A are both 0.
These are both 0. So this is this little secant line from the origin up to the point on the curve.
Yeah.
Cauchy mean value theorem, or just a little bit of geometry, you see, there are several points here on this curve where the slope of the curve is just parallel to this. So for instance, I have this point here.
Oh, here we go. Cauchy mean value,
Cauchy mean value theorem.
right?
The slope of this guy is f prime.
Of
That's a point
C in between 0 and T.
Times g prime of c. Okay,
Oh, okay.
so I had an a, I had a t, and c was somewhere in between.
Oh, and this line, this tangent slope is parallel to our secant simple slope, and therefore we can use the fact we subtract them, we did all that to get the result.
Exactly, so this thing, this is the ratio of the derivatives. And now as t gets closer and closer to a, as t gets closer and closer to a, I get down this curve here, that means my c also gets closer to a. C is getting squished between t and a, so it all goes down to a. So as this, as t gets close to a, this thing gets close to L, so therefore this thing gets close to L.
And we're done.
We're done.
That's L'Hopital's rule.
L'Hopital's rule.
Now, yeah, okay, that's fantastic. That's absolutely fantastic.
So, and again, great example. Now, there's another version of L'Hopital's rule where instead of these things being equal to 0, you can have the case where f and g are growing without bound. So f might be something like 1 over x or something like that.